A signal perfectly localized in time possesses an infinite bandwidth in the frequency domain. This fundamental trade-off is not a limitation of measurement equipment, but an inherent property of Fourier analysis and real variables. We call this the uncertainty principle. We begin in the space of square-integrable functions, denoted as L2 of the real line. Every physical state is represented by a complex-valued wave function within this vector space, where the inner product is strictly defined. For a function to represent a physical probability, the integral of its absolute square over all real space must equal exactly 1. This normalization ensures that the total probability of finding a particle anywhere is unity.
The position operator acts on the wave function by simple multiplication with the independent variable x. It maps a function to a new function where every point is scaled by its own coordinate value along the real axis. The expected value of position is the inner product of the wave function with the result of the position operator. Mathematically, this is the integral of the conjugate wave function times x times the wave function itself. In the position representation, the momentum operator is defined as -I times the reduced Planck constant times the first derivative with respect to x. It quantifies the rate of change of the phase of the wave function.
To find the expected momentum, we integrate the product of the conjugate wave function and the derivative of the wave function. The reduced Planck constant and the imaginary unit scale this value into the units of physical momentum. The Fourier transform serves as the bridge between position space and momentum space. It decomposes the spatial wave function into a sum of complex exponentials, each representing a distinct state of definite momentum. Variance measures the spread of a distribution around its mean. For position, it is the expected value of the operator x squared minus the square of the expected value of x. This represents our spatial uncertainty. The standard deviation, or delta x, is simply the positive square root of the variance. It provides a linear measure of how much the particle position deviates from the average position in a given state.
In quantum mechanics, the order of operations matters. The commutator of two operators A and B is defined as the difference between the product AB and the product BA. Non-zero commutators imply uncertainty. Applying the position and momentum operators to a test function reveals that they do not commute. The result of position times momentum minus momentum times position is exactly I times the reduced Planck constant. The proof relies on the Schwarz inequality for inner products in Hilbert space. It states that the square of the absolute value of an inner product is less than or equal to the product of the norms. For any two operators, the product of their variances is bounded by the square of the expectation value of their commutator divided by 2i. This imaginary component arises from the self-adjoint properties of the operators.
By substituting the commutator of x and p into the general uncertainty relation, we find the product of standard deviations must be greater than or equal to the reduced Planck constant divided by 2. Gaussian wave packets are unique because they satisfy the equality condition exactly. For these specific distributions, the product of position and momentum uncertainty reaches the absolute minimum allowed by the laws of physics. As time progresses, a free particle wave packet will spread. While the momentum uncertainty remains constant, the position uncertainty grows, demonstrating how the spatial localization degrades as the wave function evolves through space. This mathematical reality is mirrored in classical telecommunications as the bandwidth theorem. A short pulse in a fiber optic cable requires a wide range of frequencies, limiting how closely pulses can be spaced without interference. In electron microscopy, the momentum of the electrons determines their wavelength. Higher momentum reduces the wavelength, allowing for smaller spatial uncertainty, and thus higher resolution when imaging atomic structures in semiconductors. A similar relation exists between energy and time. The finite lifetime of an excited atomic state creates an inherent uncertainty in the energy of emitted photons, leading to the natural broadening of spectral lines. Because position and momentum cannot both be zero, a confined particle must always possess a minimum kinetic energy. This zero-point energy prevents atoms from collapsing and ensures stability in the microscopic world. In modern semiconductor manufacturing, ultraviolet light with extremely short wavelengths is used. This reduces spatial uncertainty during the etching process, enabling the creation of transistors only a few nanometers in size.
Radar systems face the same limit. Short pulses provide excellent distance resolution but poor velocity detection. Long pulses allow for precise Doppler shifts and velocity measurements, but lose precision in target distance. Ultimately, the Heisenberg uncertainty principle is not a statement about human ignorance or faulty tools. It is a rigorous consequence of the geometry of Hilbert space and the fundamental behavior of wave-like systems. The principle is deeply related to the Nyquist-Shannon sampling theorem. To accurately reconstruct a signal, the sampling rate must be at least twice the highest frequency present in the bandwidth. Physical observables are represented by self-adjoint operators. The fact that many pairs of these operators do not commute is the defining feature of quantum mechanics that separates it from classical physics.
By treating wave functions as vectors, we use the geometry of the inner product to find the minimum possible product of widths. Real analysis provides the tools to bound these integrals precisely. In a quantum harmonic oscillator, the ground state reaches the uncertainty limit. The balance between the potential energy and the kinetic energy dictates the exact shape of this minimal uncertainty Gaussian state. In classical mechanics, a particle occupies a point in phase space. In the quantum regime, a particle must occupy a minimum volume of at least h⁻², prohibiting the existence of points. In signal processing, the Gabor limit defines the best possible simultaneous resolution in time and frequency. This is the direct engineering application of the Heisenberg uncertainty principle to modern digital communications.
Scaling a function in the spatial domain by a factor a will scale its Fourier transform by 1/a. This inverse relationship is the mechanical engine behind the uncertainty product remaining constant. The smoothness of a wave function in position space determines the decay rate of its momentum distribution. A discontinuous function requires high-frequency components to resolve the sharp edge, increasing momentum uncertainty. The linearity of the expectation value operator allows us to shift our coordinates so that the mean position and mean momentum are zero, simplifying the calculation without changing the variance. To evaluate the commutator expectation, we use integration by parts. Assuming the wave function vanishes at infinity, the boundary terms go to zero, leaving only the integral that yields the physical constant. The reduced Planck constant sets the scale of the microscopic world. If it were zero, position and momentum would commute, and classical physics would be a complete description of reality. Measurements of quantum systems are inherently stochastic. The uncertainty principle dictates the width of the distribution of results we would obtain if we measured the same state repeatedly in identical conditions. Momentum is a non-local property because the momentum operator involves a derivative. Knowing the momentum precisely requires information about the wave function across all space, precluding local position knowledge. Squeezed states of light use the uncertainty principle to reduce noise in one variable at the expense of another. This technique enhances the sensitivity of gravitational wave detectors like LIGO. Rather than a limitation, the uncertainty principle is the structure that gives matter its volume and stability. It is the mathematical bridge between wave mechanics and the discrete nature of quantum reality. By applying rigorous calculus to wave functions, we uncover the fundamental bounds of the universe. The Heisenberg uncertainty principle stands as a triumph of real analysis in describing the physical world.